All right, in the last lecture, we talked about the layers that are in the sun, and we talked about the first layer, which is the core. Above that, we have another layer, which you call the radiative zone. And then above that, we have the convective zone. Then this is actually inside. Then the atmosphere of the sun, we have the photosphere, the chromosphere, and then the corona. We can say that this is 4, this is 5, and this is 6. And we talked about some of these effects, and we talked about solar wind. And we said that in this lecture, we'll talk about nuclear fusion from the sun. And now there are, when we talk about the nuclear fusion, there is something also called the nuclear fission, okay? So I don't want you to confuse these two. Fusion, that means you're taking things and you fuse them together. Fission, that means you break things apart. So what we will try to discuss here, we'll basically look at the energy production in the sun. Now, the energy generation in the sun, and of course that applies to all stars, is done with something that we call nuclear fusion. And fusion, maybe بالعربي اندماج, okay. Fusing together two or more light nuclei to produce heavier ones. So that's what fusion is. Now we look at the x-axis here, and we have binding energy due to strong forces. And this is actually on what we call the short range, strongest of the 4 known forces. We have something that we call electromagnetic forces, weak and strong. And then we have gravitational forces. Now, this binding energy or nuclear forces that basically are the strongest, and this happens inside the nucleus. Now, when we look at how can we proceed with elements, can we combine elements to produce fusion? Okay. So the idea here, you go down this line, and that's basically what we say here, fusion. So you can go from hydrogen, you can get lithium, helium, nitrogen, carbon, oxygen, and you get to iron here. So inside stars, element can produce up to iron with nuclear fusion. Now, elements that are higher than iron, we gain energy from them by nuclear fission. That means you take something like uranium or plutonium, and then you can break it. And once you break it, you're going to get what? You're going to get energy. So this is, before we start from here, in the sun we're basically taking hydrogen to produce helium, but in the very big stars, we can go all the way up to iron. But if we want to produce nuclear energy, then we have to go for elements that are higher than iron, then we have to basically rely on fission. And fission maybe بالعربي نقولها انشطار. So that's basically the energy that we can produce from nuclear energy. So let me just, maybe you've seen a famous equation, which is E equals mc squared. That means energy is related to mass multiplied by c squared. And that's what Einstein basically found, a relation between mass and energy. So sometimes mass is related energy divided by c squared. Now, the basic idea for nuclear fusion, if you take, let's say in general, if we take A and you take B, and then you combine them together, that means you're basically combining the nucleus from each atom. Now, if I will get something, which is here, I will call it C. It will result in C. The mass of C is going to be less than the mass of A plus the mass of B. So I lost some mass. This mass that I lose, it will become in energy in accordance with mc squared. That's in the case of fusion. In the case of fission, if you take an atom, let's say A, and then you split this atom, you will have B and you will have C. The mass of A, it's going to be greater than the mass of B plus the mass of C. So I lost some mass in the process. And this mass, of course, will go as E equal to mc squared. And remember, these are coming from the nucleus. And in the nucleus, we have very strong nuclear forces that hold the protons and neutrons inside the nucleus at a very small distances. So they're very short range. So either we are doing nuclear fusion or nuclear fission, we always end up with less mass. And the mass that is basically we lose, it goes into energy. So if we want to produce energy by fusion, we have to basically, inside stars, you can go all the way up to iron. You're fusing basically the nucleus inside. Now, iron, it becomes very tight, so it's not easy to jam anything. You need more forces to do that. But we can go the other way, and we basically start here with fission. Now, inside the sun, what we have is we have nuclear fusion. And the basic idea that we have inside the sun, that we start from a basic reaction, which we need 4 hydrogen atoms, and it will give me a helium atom plus energy. Why is that? Because if I look at the mass of 4 hydrogen atoms, I multiply the mass of 1 hydrogen atom by 4, and then I look at the product here, which is helium. And I look at the mass of helium, and you can do that by looking at a periodic table. If you have a periodic table, just look at the atomic mass of hydrogen and multiply that by 4. And look at the mass of helium. You'll find that the mass of helium is less than 4 times the mass of hydrogen. So in the process, you lose energy. And that energy basically will become energy that you gain as in the form of mc squared. Of course, here we say delta M, and delta M is the difference between the starting mass and the resulting mass. So a reaction like this will give me something like 0.43 times 10 to the 11 joules. But inside the sun, there are about 10 raised to the power 38 reactions, transforming about 5 million tons of mass into energy every second. That's to resist the gravity. Gravity will try to bring the sun in, and this energy it's produced and it's pushing out. So that's the basic idea. So how do we proceed with this? And that's why we say here proton-proton chain. So how we actually go with this? Now, let me basically tell you about the state. You all learn that in school. You say that you either have gas, liquid, or solid. There is another fourth state, which we call plasma. And I don't want you to confuse that with blood plasma. And a plasma is basically when you strip the atoms out of the electrons, so it becomes highly ionized. And that's what's happening in the sun. It's really hot and so on, so we have plasma. Now, when we talk about hydrogen, hydrogen is the lightest element, or the smallest element. And hydrogen has a nucleus, and inside the nucleus, you have a proton, one proton. So you have to remember that. In hydrogen, you don't have, inside the nucleus of hydrogen, you don't have a neutron. You have one proton. And around it, you have an electron. So in the idea of the fusion here, we're going to bring two hydrogen atoms. Of course, they're stripped out of their electrons, and you try to fuse them together. So you're trying to fuse the nucleus of each atom. And of course, each one contains a proton. And the proton is positively charged. So there is a positive charge here, positive charge here. When you try to force these together, they will repel one another. So you have to have a greater force to overcome this. And this is what we call Coulomb repulsion. Coulomb found that there is a force of attraction between positive and negative charges, or repulsion force between like charges. Like when they're both are positive, they will repel, and when they are both are negative, they will repel. But if they are unlike, then they will attract one another. In our case here, inside the nucleus of the hydrogen atom, which we only have in each one now proton, the protons are positive, so they will repel one another. And if they repel one another, we need something to force them in. So we need a very high temperature, and we need a temperature more than 10 million degrees to do that. Inside the core of the sun, the temperature is about 15 million degrees, so it can allow for the fusion to take place. So what happens when these two hydrogen fuse together? And that's why you say proton or proton, because it's basically now the nucleus has only one proton. Now, when that happens, I want you to pay attention here. The red sphere here, we call it a proton. So when you look at this diagram here, the gray is a neutron, and you know that neutrons are basically neutral. They don't have any charge. And then you have here the purple color is positron, and positron is opposite to electron. It has similar mass, but it has a positive charge, not a negative charge. Now the blue here, now this is energy. It's not a particle. So you have here gamma rays, and you have here something that we call neutrino. It's a very small particle. So when you actually bring in these two hydrogen nuclei together, and the temperature is overcoming the Coulomb repulsion, so they can fuse together, well, neutrino is produced, and positron is basically coming out, and that's a positive charge. And that's how now we get what we call deuterium, which is hydrogen 2. So inside the nucleus now of the hydrogen, we have one proton and 1 neutron. That means one of these protons have been converted to neutron by emitting a positron. Of course, there is neutrino as well produced in the reaction. The step after that this deuterium with another hydrogen atom, they combine. Of course, the temperature is there to force them, because we have 15 million now. Maybe you need higher temperature, but you still have this 15 million degrees that can allow that. And there is an emission of gamma rays, and then you get something here which you call helium-3. Now, helium, inside the nucleus of helium, you have 2 protons and 2 neutrons. But here, what we have is, we have only 1 neutron. Now, remember, when we discussed chapter number 6, I told you that when you look at an element, the number of electrons, which gives me the atomic number, determines what type of element it is. So here I have 2 protons. And 2 protons here tell me that this is now helium. But it's an isotope of helium. It is helium-3. So you start with 2 hydrogen atoms, and you end up basically getting helium-3 here. Now, you can also have another process. That's why we call it a chain reaction. It's 2 hydrogen nuclei that basically will emit positron and neutrino, and then they give you deuterium, and deuterium with hydrogen, they emit gamma rays, and you get helium-3. Now, 2 helium-3s, they combine. They actually, 2 protons will exit, and then you have here helium-4, which is 2 protons inside and 2 neutrons inside the nucleus. That's why we call it proton-proton chain reaction. So the basic idea that we told you here, you start with 4 hydrogen atoms, and you're going to produce helium atom, and of course the difference in mass will come in as energy. That's exactly how the sun is producing its energy. Now we say here the 4 protons, that means the mass of the 4, it's more than the mass of the helium itself, and I have a difference in mass. If I multiply that by c squared, that will give me the energy produced by this reaction. But of course, the sun makes 10 raised to the power 38 reactions, transforming about 5 million tons of mass and energy every second. That, of course, will push out, applies a pressure outward. And gravity will try to bring the mass inward, and that's how the star or the sun becomes what becomes a stable star. Now for this, as I told you, we need high temperature to overcome what we call the Coulomb barrier. And the Coulomb barrier is electrostatic repulsion between protons. Now, Coulomb, if you have 2 charges separated by distance r, he said that the force between them, it's Q1, Q2, let's call this 1 and 2, over r squared. So you can see as this number becomes small, this number would become very high. And that's why when you have these 2 positive charges and you try to bring them, you know that the size of the nucleus, it's on the order of 10 raised to the power minus 15. It's a very small distance. So you need a large force to do that. And that's why we need this high temperatures. And that's what we call the Coulomb barrier. Actually, it is electrostatic repulsion between protons, because the protons have positive charges, and I explained what is proton-proton chain is. So you can basically pay attention to this reaction here, and that's basically the reaction that the sun is using to produce the energy. Of course, as we discussed in the last lecture, this is produced in the core, then it's radiated through the radiative zone, and you can see the gamma rays, that's the energy is radiating out because the sun is made of gases, and then it comes to this layer here where you have the convective zone that we talked about. So the hot gas will rise up, which is in red here or violet, and then the cooler gas basically comes or sink on the edges, and that's how you form the bubbles that we see on the convective zone. So that's basically, we talked about these three layers, which is the core, and then the radiative zone, and then we talked about the convective zone. That's how the sun is generating its energy, and then it's transported through the radiative zone, then it comes to the convective zone. And I told you above the convective zone, you have the photosphere, and we talked about the atmosphere of the sun. So that's how the sun is generating its energy. Here we dream of this because you actually taken hydrogen and you're producing helium. Helium is not harmful. Unlike nuclear fission that we use here on Earth, the nuclear fission that we use here, we use either uranium or we use plutonium, and you split that and you get a nuclear waste, and that's dangerous and it's radioactive. And how can you take care of that? You have to put it in big barrels and you bury it somewhere, or you drop it in the sea, and it takes a very long time. Remember when we talked about half-life time, when we talked about radioactive decay. So that's something which it takes a very long time to fully radiate all the energy. So here we think of nuclear fusion. So let me just share my whole screen with you. I want to take you to a comparison here. This is from the Office of Nuclear Energy, and they give you here a comparison, so we'll try to go through it, between fission and fusion and what is the difference. So in fission, you're basically splitting. Atoms. Fusion, you're joining atoms. So that's a difference now. Now, you're using uranium or plutonium. Here you're using hydrogen. Here you're producing waste. Here you're producing helium in fusion. But this is already, we use in nuclear reactors, but this is under development. This is what we get. With the fusion, we get more, greater energy. So now there is a push for fusion energy. But the problem is, you need very high temperatures. And you need to confine the plasma to do that. Now, this is what we call the tokamak. It is a design where you can basically use magnetic field to confine the plasma. And if you can do that, then you're going to be able to produce energy. So you can see how big these are. That's basically a Chinese, sorry, it is a Russian design. So they use magnetic fields to confine the plasma. They need the heat, but they have to confine it. And of course, these are made with something that we call superconductors, a subject that is dear to my heart. I like superconductivity a lot, but that's the material that's used in making these high magnetic fields to confine the plasma, which then you can produce the energy from. Now, there are major breakthroughs in this, and probably in the future, we'll see nuclear fusion taking place. I think in China now, they're making some progress. In Europe, I think in France, they have, I think, the biggest one. But in China now, I think there are some news coming out. And I even heard that in China, they're going to suspend subsidies on wind and solar energy. Maybe they're looking at some sort of nuclear fusion in the future. So that's now why here on Earth we are trying to produce what we say, what's happening inside the sun. So to summarize this part here, how does the sun make its energy? The sun generates its energy through nuclear fusion, during which hydrogen nuclei fuse to produce helium nuclei. Hydrogen fusion in the sun proceeds in 3 steps known as the proton-proton chain. And I showed you that proton-proton chain. Fusion can occur only at the center of the sun because charged particles repel each other, and high temperatures are needed to penetrate the Coulomb barrier. And I told you about the Coulomb force. Of course, this is in the first of these 3 steps on quantum mechanical effects. We get deuterium. Deuterium is basically hydrogen. It's still hydrogen, but inside the nucleus now you have a proton and a neutron, a heavy isotope of hydrogen. Energy is produced as positrons, neutrons, and gamma rays. That's the energy that we get out. It will come out as positrons, neutrons, or neutrinos, or gamma rays. That's what goes through the radiative zone, and then it will come to the convective zone. Energy flows out of the sun's core as photons. Remember, we talked about electromagnetic waves. So these are photons traveling through the radiative zone and closer to the surface as raising currents of hot gas in the convective zone. That's how the sun works. And we're lucky enough that we learned that about the sun. Of course, we can extrapolate and we say that other stars work in the same way. Of course, there are bigger stars. We'll talk about that in chapter number 9. So inside the sun, basically, they go to helium. But in other stars, they can basically go as high as iron. So even the elements that in your body, they were once produced inside stars. So that's one way to look at this. And now here on Earth, we're basically trying to recreate this and to produce nuclear reactors that work with fusion. But of course, you have to confine the plasma. And I told you that there is a fourth state of matter now. We talk about gas, liquid, solid, but we also can talk about the plasma. In plasma, it's basically when you strip the atoms out of the electrons. It become highly ionized. We call this plasma. If you confine this plasma with high magnetic fields and you heat up, then basically you can, or you'll be able to do this. Now here on Earth, just to give you something, they are not basically using in the fusion. They use deuterium of hydrogen, because this is one isotope that can be found in seawater and so on, and thorium. So these are things that are used now. So that's how the sun is producing its energy. Any question on these? Is this clear? Is this clear? Now, then we're going to look at the solar activity. And the first thing that we're going to look at sunspots. Because we see that on the surface of the sun. So why do we see these sunspots? So scientists were paying attention to these sunspots. So that's basically, they tell you here, that's the size of the Earth, and you can see how big these sunspots are relative to the size of the Earth. The sun is huge compared to the Earth. Now, one piece of information came, and there are techniques where temperature can be measured. We don't have to go to the surface of the sun. There are techniques that we can do here from the surface of the Earth. Now, the average surface temperature of the sun is, as we discussed in the last lecture, 5,800 Kelvin. Now, when you look at a region where you have sunspots, the temperature there is about 4,240 Kelvin. So they are lower in temperature. So the reason that we may see them as dark here is because of this contrast in temperature. The surface of the sun is 5,800 Kelvin. These are 4,240 Kelvin, which is still very hot. But that's why, as we say here, appear only dark against the bright sun. And if you really, if you take the surface of the sun away, they're very bright, okay, because they're very hot. But they only appear this way because in the background of the surface of the sun. So that's one piece of information now. Now, why, a question that can be asked, why the temperature here is lower than the rest of the surface of the sun? So the first piece of information that was basically collected, that sunspots, they have lower temperature than the surface of the sun. Now, that's if you use visible light and you can see these sunspots. That's if you do ultraviolet. You put a filter or you try to look at the ultraviolet and you can see the granulation or the convective zone clearly. These regions basically look whiter here because you're looking in a different wavelength. Now, if we look at the X-ray, that means we want to look if the sun is producing any X-rays, and that's what we call out the soft X-rays. You can see some activities here. Remember what we did in chapter number 5. We talked about the electromagnetic waves. And we said that they all have the same speed, which is the speed of light, which is a frequency multiplied by wavelength. But we also talked about energy, and we said the energy is equal to hf, frequency. So these are basically come out of some processes in the sun. So if we, I will try to give you here something that was taken for a period in 2011. You can look at NASA website and you can basically look at how NASA monitors the sun. The sun is basically rotating, and this is an ultraviolet image that you can see basically how the sun is active and producing these effects there. So this is the sun is active, producing all of these electromagnetic waves that come toward, and we can study all of these. So when it comes to sunspots, we learned that the temperature is lower. Another piece of information became available is when we try to look at the magnetic field of the sun. And when you look at the sunspots, the magnetic field there is 1,000 times stronger than average. That means these regions there, they have a stronger magnetic fields. And of course, these magnetic fields seem to be emerged out of the photosphere, which is the sun. So in that region, the temperature is cooler and the magnetic field is higher. So what is the connection between these two? Now, when you probably played with this, you take a magnet bar, you put a piece of paper on top, and then you bring iron filings, and you actually, they can trace the magnetic field lines. So there is something beyond the magnet itself. This is the magnet here. But these magnetic field lines, they extend beyond the boundary of the magnet itself. And that's why we say this magnetic field is real. That's why we call it a field. And usually, these magnetic fields will go from north to south. And they basically loop like this. Now you may, I just probably add something here that you may hear that people talking about monopole. And monopole, that means one pole. Now if you break this magnet in half and you repeat, it will give you the distribution of these magnetic field lines. So there is no monopole. Even if you break this, you will still have north and south. You break it, it will have north and south as well. So these are basically what magnetic field lines look like. Now, when it comes to the sun, and we talked about that when we talked about the corona, and we said why the corona is very hot. We see that hot gas is ejected from below, and that's very hot. It does not go through the process where it cools, like what's happening in the convective zone. It shoots out, and it follows something like this, which is basically resembles the shape of magnetic field lines, because magnetic field lines, they have to start from a pole and end up on another pole. So this basically has to do with the structure of the magnetic field of the sun. And it gave evidence that yes, we have magnetic field lines. Material can basically loop out of the sun and then comes back, and that's why the corona is very hot. But what's happening in these regions there? So the idea here is that the magnetic field, which is stronger, 1,000 times stronger, where you have a sunspot, the material that it's there, the magnetic field is going to inhibit their motion. It's going to make it slower. So unlike the rest of the surface of the sun, where we have convection and the hot gas is rising and the cooler gas is coming down, well, in the region where you have a sunspot, the gas is not allowed to go as fast, the rising gas, and it stays for longer. And that's why it cools to a lower temperature. And when you compare that temperature to the rest of the surface of the sun, then that's why it looks like sunspots. So since Galileo Galilei spotted them, scientists became interested and they want to learn. Actually, in the process, these sunspots seem to have a cycle, and they have 11-year cycle. So scientists were looking at the number of sunspots, or the maximum number of sunspots. Something interesting was found, that the sunspots is not something static, it's moving. And it varies between a minimum and a maximum value. It doesn't have to be the same number, the same maximum number, but there seem to be a minimum and a maximum, a minimum and a maximum. And of course, between these two maxima, you actually, it happens every 11 years. So you do that. Now, there was an explanation, why does it do that? And the reason for that, it's the magnetic field of the sun reverses polarity. So it will go from the north will become south, and the south will become north. And that's when you hit basically another maximum. In the middle, of course, it will be in the reversal between these, you will get a minimum. Then what we call the total cycle, it will be 22 years. That means you have north, south, then you will have south, north, and that's 11 years. Then it will go back again to north, south, and that needs another 11 years. So in total, you have 22 years. And that's why we call the full cycle is 22 years. And that's basically because of the reversal of the magnetic field of the sun. It's moving. Unlike the permanent magnets that we have here. That's why we call them permanent magnets. This one, no, it's moving. Now, sunspots, basically the data that collected, it can go as back as 1750. And you can look at the data as it's going through a maximum and a minimum. So it will basically go through that every 11 years. So I think here we had the maxima in 2001, then 2012, and we'll have another one in 2023. And that basically comes as a result of the sunspots of the sun. So the sun is very active, and these sunspots basically come as a result of the activity of the sun. Mandarin start looking at the sunspot as a function of latitudes. So you look at the sun, like what we said in the earth, you have the equator, and then you have different latitudes here. He found something very interesting. If he plotted the data, and something that came out which resembles like a butterfly wings. And that's why this was known as the Mandarin butterfly diagram. So he's just plotting above the equator and below the equator. You see the 0 here, then 30 north up to 90 north, 30 south up to 90. So we're basically going as a function of latitude, and that's what he basically found. So sunspots starts out with the spots at higher latitudes on the sun and evolve to lower latitude toward the equator throughout the cycle. And that's what Mandarin basically found out. Now again, this is if you take the total number, okay? And now you go back to the 11-year cycle here. So that was basically the idea here of the sunspot. The sunspot basically comes as a result of the magnetic field of the sun and how the sun is generating this magnetic field. And in some region, this magnetic field becomes higher than the rest, and it holds the convective process for longer, and that's why the gases in that region will become lower. There is something that's known as the Mandarin minimum, and it happens between 1650 and 1700. While it's still showing maximum and minimum in the sunspots, but it seems to be basically lower. And some are argue that maybe the sun will go through times where it has low activities. And this is what say the quiet phase maybe of the sun, but it's still, there are some that doubting that, but actually the sun at sometimes it is very active, at sometimes maybe it's less active. So this is basically the sunspots. They actually come as a result of the magnetic field that we have in the sun. So how does the sun produce its magnetic field? And we call here the magnetic dynamo. Any of you who rides a bicycle, especially at night, you have headlight in the front, use something in the back wheel that we call a dynamo, and that dynamo basically produces electricity for you. Now, when you look at dams and things like that, water will rotate something, and you have magnetic fields at the end, and that's how you can basically produce what? Produce electricity. I will take it from here, but I will just want to tell you something, that the subject of electricity was on its own, and magnetism was on its own. Then finally, it was discovered that when you have a current through a wire, that current will produce magnetic field. And if you have a compass with you, just go close to any wire that's connected to electricity, and you will see that the needle is basically deflected in different directions. So moving charges, which constitute electrical current, they can produce magnetic field. So in the next lecture, we'll talk about it is the rotation of the sun, and you basically have these ionized gases that can give you electrical current, and the electrical current produces magnetic field, and we'll talk about the structure of the magnetic field of the sun. Any questions on these? Any questions? Any questions? Good.